Hello, stargazer. Welcome back to another quiet journey through the cosmos. It's good to have you here. There's a photograph that exists somewhere in the archives of human memory. A pale blue dot suspended in a sunbeam. Tiny, fragile, alone in the vastness. When you look at that image, Earth seems so obviously special, so perfectly strange in all the right ways. But what if I told you that Earth might be the strangest planet we have ever found? Not because of what it has, but because of what it lacks. What if the rain here is the anomaly? What if having just one sun in the sky is the cosmic oddity? What if we've been living on the universe's most peculiar world all along, and we simply never knew it? Before we drift into the deep tonight, I want to invite you to stay a little while longer. If these quiet explorations bring you comfort, you might like to gently tap the like button below. Subscribe if you'd enjoy more of these soft-spoken journeys among the stars, and consider ringing the bell not for noise, but so the next calm night can find you when you need it most. Thank you for being here. Now, let's begin. For most of human history, we believed Earth was the center of everything. The sun, the moon, the planets, all of them circled us in perfect crystalline spheres. It wasn't arrogance, not entirely. It was the only story that made sense when you looked up and saw everything moving around you. Ptolemy mapped it. The church sanctified it. Philosophers taught it for 1,400 years. Earth wasn't just special. It was the foundation of all creation. Then came Copernicus, quietly, cautiously suggesting that perhaps we circle the sun instead. Galileo turned his telescope upward and saw moons orbiting Jupiter, tiny worlds that had nothing to do with Earth at all. The center shifted. We became one planet among several, all bound to the same star, all following the same rules. And for a while that felt like the end of the story. We knew our place. We understood our neighborhood. We thought we knew what planets were supposed to be, but we didn't. Not really. For centuries, the only planets we knew were the ones we could see. Mercury scorched and swift, Venus cloaked in acid clouds, Mars cold and red and silent, Jupiter vast and stormy, Saturn with its rings of ice, Uranus and Neptune distant and blue. 8 worlds if you count Earth. 9 if you remember when Pluto still belonged. They were different from each other, yes, but they fit a pattern. Rocky planets close to the sun, giant planets farther out, moons where moons should be. It all made sense the way a family resembles itself. And then we found the others. October 6th, 1995. 2 Swiss astronomers, Michel Mayor and Didier Queloz, announced something impossible. They had found a planet orbiting a star called 51 Pegasi, about 50 light-years away. This wasn't remarkable by itself. Scientists had suspected other stars might host planets for decades. What was remarkable, what shattered every model we had, was where this planet was. It was massive, half the size of Jupiter, but it orbited its star every 4 days. 4 days. Mercury takes 88. This giant world was closer to its sun than Mercury is to ours, so close that its surface temperature likely exceeded 1,000 degrees Celsius. It shouldn't have been there. Gas giants form far from their stars, where it's cold enough for ice and gas to accumulate. That's what our models said. That's what Jupiter and Saturn proved. But 51 Pegasi b didn't care about our models. Scientists called it a hot Jupiter. The name stuck even though it felt inadequate. Hot doesn't quite capture a world where the air itself might glow, where metals vaporize and wines scream faster than sound. But language fails at the edges of understanding. We name things to hold them still, to make them manageable. The universe doesn't always cooperate. That discovery opened a door we didn't know was closed. Within a few years, we found dozens more exoplanets, then hundreds, then thousands. The Kepler Space Telescope, launched in 2009, stared at a single patch of sky for 4 years and found over 2,700 confirmed planets, with thousands more waiting for verification. As of now, We've confirmed more than 5,600 planets beyond our solar system. Each one is a data point. Each one tells a story. And many of those stories make no sense at all. Some planets orbit their stars backward. Some are tidally locked one face forever, burning the other, frozen in eternal night. Some have years that last mere hours. Others take millennia. We've found planets made of diamond planets covered in oceans hundreds of miles deep. Planets where it rains molten glass sideways at thousands of miles per hour. We've found planets that shouldn't exist, orbiting stars that should have destroyed them, defying physics in ways we're still struggling to explain. Here's what we're learning, slowly, uncomfortably. Earth is not the template. Earth is not the median. Earth might be the exception, a strange little accident in a universe full of extremes. We have liquid water on our surface. Most planets don't. We have a stable climate that's persisted for billions of years. Most planets don't. We have one moon, one star, a magnetosphere that shields us an atmosphere that doesn't crush or poison us. These aren't universal features. They're rare privileges, cosmic coincidences we took for granted because we had nothing to compare them to. And perhaps that's the strangest part. We spent so long thinking we were ordinary, unremarkable, just one small world among countless others. We worried we weren't special enough. But the more planets we find, the more we realize how peculiar our home truly is. Not because it's grand or large or impressive, but because it's gentle, because the rain here is water, because the sky is blue, because you can stand on the surface without being crushed, melted, frozen, or torn apart by winds that could strip flesh from bone. Do you ever think about that? How much had to go exactly right for you to exist here? Breathing easily, listening to these words. It's not just biology, it's geology, chemistry, orbital mechanics. A planet at the right distance from the right kind of star, with the right kind of moon to stabilize its tilt, with the right kind of magnetic field to hold its atmosphere. Change any one variable, and Earth becomes something else, somewhere you couldn't live. We used to think planets were rare. Then we found them everywhere. We used to think planets like Earth were common. Now, we're not so sure. The more we look, the stranger the universe becomes. An Earth quiet, temperate life. Bearing Earth starts to look less like the norm and more like a beautiful anomaly, a fluke, a stroke of luck we're still trying to fully comprehend. Tonight we're going to visit some of those other worlds, the ones that break the rules, the ones that make scientists pause and recalculate, that force us to rewrite textbooks and reconsider what we thought we knew. We're going to drift through skies where glass falls like rain past oceans that burn without boiling around suns that should not have planets but do anyway. We'll meet worlds older than time should allow, darker than shadow, wandering alone through the void, with no star to call home. You don't need to understand all of it. You don't need to remember every name or number. Just let the strangeness wash over you. Let it remind you how vast and varied creation truly is. How many kinds of worlds are possible. How fortunate, how statistically improbable it is that you were born on one of the gentle ones. Some nights when the sky is clear and the stars feel close, it's easy to forget how much emptiness lies between them, how cold it is out there, how hostile, how indifferent the universe is to whether we thrive or perish. But we're here anyway, against all odds on a planet that happened to be just right, looking up at worlds that remind us how easily it could have been otherwise. Maybe that's what makes these discoveries so compelling. They're not just about science, they're about perspective. They're mirrors held up to our own world, showing us what we have by showing us what we don't. Every scorched wasteland, every frozen hellscape, every impossible planet we find makes Earth feel a little more precious, a little more worth protecting, a little more like home. And so, we drift onward past the familiar into the strange. Let's talk about the planets where the sky is full of glass and the rain can cut you to pieces before you even feel it fall. Imagine standing beneath a sky where the clouds aren't made of water vapor, but of molten silicate particles suspended in superheated air. The wind howls at 7 times the speed of sound, and when the rain falls, it doesn't patter gently on leaves or drum softly on rooftops. It cuts, it shreds. It falls sideways at 400 miles per hour, each droplet a tiny shard of glass heated to over 2,000 degrees Fahrenheit. This isn't science fiction. This is HD 189733b, a planet astronomers discovered in 2005, orbiting a star 63 light-years from Earth. A world where the weather can kill you in ways you've never even imagined. HD 189733b looks deceptively beautiful from a distance. When astronomers first studied it using the Hubble Space Telescope, they found something remarkable. The planet appears deep blue, almost cobalt, strikingly similar to Earth when viewed from space. For a brief moment, that color sparked something in us, didn't it? A flicker of recognition, a sense of kinship across the void. But that blue isn't from oceans. It's not from an atmosphere rich in nitrogen and oxygen. It's from silicate particles scattering light in the upper atmosphere, the same particles that will later rain down as molten glass. Beauty and brutality wrapped in the same wavelength of light. The universe has a dark sense of irony sometimes. This planet is what scientists call a hot Jupiter, similar to the one we mentioned earlier, but with conditions even more extreme. It orbits its parent star once every 2.2 Earth days, completing a full year faster than we complete a weekend. It's tidally locked, meaning one side perpetually faces the star, while the other remains in eternal darkness. The day side reaches temperatures around 1700 degrees Fahrenheit. The night side, deprived of any warmth, drops to a comparatively frigid 1000 degrees. That temperature difference creates winds. Violent, relentless supersonic winds that scream across the Terminator line the narrow border between day and night, carrying heat and particles and chaos in their wake. Here's where it gets strange. The atmosphere on HD 189733b contains silicate compounds similar to the quartz in sand or the minerals in certain types of volcanic glass. Under normal Earth conditions, these would be solid, inert, harmless. But on this planet, the temperatures are so extreme that silicates vaporize. They exist as a gas in the atmosphere, condensing into tiny particles as they rise into cooler upper layers. Then gravity pulls them down. They fall as rain, but the winds catch them, accelerate them, hurl them horizontally across the planet at speeds that would turn them into microscopic bullets. Scientists suggest that standing unprotected on HD 189733b would be like facing a sandblaster filled with molten glass shards, each one moving faster than a fighter jet. Your body wouldn't just be damaged. It would be scoured away molecule by molecule until nothing remained. And yet, in a strange way, this planet taught us something beautiful. Before we discovered HD 189733b, we thought we understood planetary atmospheres fairly well. We had models, we had equations. We assumed that atmospheres behaved in predictable ways, circulating heat, distributing pressure, settling into stable patterns. HD 189733b shattered those assumptions. It showed us that atmospheres can be weapons, that weather can exist in forms we'd never conceived, that the gentle rain we experience on Earth, the rain that nourishes crops and fills rivers and taps softly against windows while we sleep, is not universal. It's a gift, a cosmic courtesy, a rare alignment of temperature, pressure, and chemistry that most worlds never experience. But HD 189733b isn't alone in its strangeness. Let's drift a little farther to a planet called WASP 76b, discovered in 2013 about 640 light-years from Earth. This world makes HD 189733b seem almost hospitable by comparison. WASP 76b is larger than Jupiter, yet it orbits so close to its star that it completes a full orbit in just 1.8 Earth days. The day side of this planet reaches temperatures exceeding 4,400 degrees Fahrenheit, hot enough to vaporize most metals. And one of those metals is iron. On Earth, iron is solid strong, the element we use to build bridges and skyscrapers, the core of our planet, the molecule in our blood that carries oxygen to our cells. We think of iron as stable, dependable, permanent. But on WASP 76b, iron doesn't behave that way. The day side is so hot that iron exists as a vapor floating in the atmosphere like humidity on a summer afternoon. But here's what makes this planet truly alien. The strong winds carry that vaporized iron from the scorching day side toward the cooler night side. As it crosses the terminator, the boundary between day and night, the temperature drops just enough for the iron to condense. And then it falls, not as rust, not as ore, as liquid metal, pure molten iron raining down in droplets that glow orange and red as they descend through the darkness, a storm of liquid fire falling from a black sky. Astronomers detected this phenomenon using spectroscopy analyzing the light passing through WASP 76b's atmosphere as it transited in front of its star. They noticed that iron absorption lines were present on one side of the planet but absent on the other. The iron wasn't disappearing. It was changing state, condensing and falling as rain on the night side, then evaporating again when winds carried it back toward the heat. A cycle, a rhythm, a kind of brutal, beautiful equilibrium. Think about that for a moment. Rain, that simple, ordinary thing we've experienced our entire lives, exists in forms beyond our comprehension. On Earth, rain is water. On Titan, Saturn's largest moon, it rains methane. On Venus, sulfuric acid condenses in the upper atmosphere, though it evaporates before reaching the surface. And now, we know that on distant exoplanets, rain can be glass iron, even rock. Scientists have theorized about planets where it rains rubies and sapphires, where corundum particles condense in the upper atmosphere and fall like gemstones from the sky. Worlds where the ground is littered with what we'd consider treasure yet utterly uninhabitable, valueless in their abundance and hostility. There's a lesson in that, isn't there? Value is context. A diamond is precious on Earth because it's rare, because we've assigned it, meaning because we can hold it and admire it without being incinerated. But on a planet made of diamond, which we'll visit later, it's just geology. Just the way carbon arranges itself under pressure. The universe doesn't care about our economics, our desires, our definitions of beauty. It simply creates endlessly and differently in forms that sometimes happen to align with what we find wondrous, and sometimes don't. Another planet worth mentioning, though, its reign is slightly less dramatic, is HD 29458b, nicknamed Osiris. Discovered in 1999, it was one of the first exoplanets ever detected, transiting its star, giving astronomers their first real glimpse into alien atmospheres. Osiris is also a hot Jupiter orbiting dangerously close to its sun, but what makes it remarkable is that it's slowly evaporating. The intense stellar radiation is stripping away its atmosphere at an estimated rate of about 100,000 tons per second. Hydrogen, helium, carbon, oxygen all boiling off into space, creating a massive comet-like tail that stretches behind the planet as it orbits. Scientists suggest this planet is dying, slowly bleeding itself into the void, and one day, millions of years from now, it might be reduced to nothing more than a naked core, a rocky remnant of what was once a gas giant. But even as it dies, Osiris reigns. The upper atmosphere, still clinging to the planet, contains sodium, which condenses and falls in trace amounts. Astronomers detected sodium absorption lines in the planet's spectrum, proof that even in the process of disintegration, even as it loses itself piece by piece, Osiris maintains some semblance of weather, some ghost of atmospheric circulation. It reigns even as it unravels. There's something poetic about that. Something quietly tragic. What strikes me most about these planets is how they redefine normalcy. We think of rain as gentle, refreshing, life-giving. We've written songs about it, poems, entire mythologies. Rain is cleansing, rain is renewal, but that's only true here. Only on this one small world where water exists in liquid form, where temperatures stay within a narrow range, where atmospheric pressure is neither too high nor too low. Step outside that range, visit any of these distant planets, and rain becomes a weapon, a force of pure destruction, a reminder that the universe operates on scales and in conditions that mock our fragility. And yet, knowing this understanding how hostile most worlds truly are makes Earth feel less ordinary, doesn't it? Makes our gentle rain, our breathable air, our survivable temperatures feel less like the default and more like a miracle. We are not living on a typical planet. We are living on an anomaly, a statistical outlier, a world where the weather doesn't kill you, where the sky doesn't scour you, where you can stand outside during a storm and feel the rain on your skin without being destroyed. How many planets in this universe can offer that? How many worlds are gentle enough for life as we know it? Not many, perhaps not many at all, but the strangeness doesn't end with rain. There are worlds where the very concept of ice becomes paradoxical, where frozen water burns, where darkness is absolute, where physics bends into shapes that shouldn't be possible. Let's drift toward those places now, toward the frozen hells and the burning cold, where intuition fails and the universe reveals just how little we truly understand. There's a planet about 30 light years from Earth where ice is on fire, not metaphorically, not poetically, literally burning, though it never melts, never evaporates, never changes state, despite being heated to temperatures that would boil water in seconds. The ice just sits there, solid, unmoving, blazing hot, defying every intuition you've ever had about how matter should behave. This is Gliese 436b, a world that shouldn't exist according to the chemistry we learned in school, yet there it is, orbiting a red dwarf star in the constellation Leo, challenging everything we thought we knew about the relationship between heat and phase transitions. Gliese 436b was discovered in 2004 using the radial velocity method, where astronomers detect the slight wobble a planet causes in its parent star as it orbits. At first, it seemed relatively ordinary for an exoplanet, roughly the size of Neptune, about 22 times Earth's mass, orbiting very close to its star with a period of just 6 Earth days. Hot Neptunes, as they are called, aren't uncommon. We've found several dozen of them scattered throughout the galaxy. But when scientists began studying Gliese 436b's composition and atmospheric properties more closely, they discovered something impossible. The planet's density suggested it was made primarily of water, but the surface temperature measured around 439 degrees Celsius over 800 degrees Fahrenheit. At those temperatures, under normal circumstances, water should be steam, vapor, gas. It certainly shouldn't be solid ice. And yet somehow, it was. The explanation lies in pressure. Extraordinary, crushing, almost incomprehensible pressure. Gliese 436b's gravitational pull is so intense that it compresses the water molecules into a state called ice 10. A crystalline form of ice that remains solid even at temperatures that would normally vaporize it. Think of it this way. On Earth, water transitions between ice, liquid, and gas based primarily on temperature. Freeze it, and it becomes solid. Heat it, and it melts, then boils. But temperature isn't the only factor that determines phase. Pressure matters too. Deep in Earth's oceans, water behaves differently than it does on the surface. Increase the pressure enough, and water's phase diagram, that chart showing when it's solid, liquid, or gas, starts to look very different. Scientists suggest that on Gliese 436b, the pressure is so extreme, perhaps millions of times greater than Earth's atmospheric pressure at sea level, that water molecules are forced into tight crystalline structures that can't break apart even when bombarded with intense heat. The molecules vibrate violently. They carry enormous amounts of thermal energy. But they can't escape. They're locked in place by the sheer weight of the layers above them. So, you have ice, hot ice, burning ice, a substance that violates our everyday experience so completely that it barely seems real. Imagine touching it if you could somehow survive the heat and pressure. Would it feel cold? Would it feel hot? Would it feel like anything at all before it killed you? These are questions we can't answer empirically. Not yet, but they're worth asking. They remind us that matter is weirder, more versatile, more adaptable than we give it credit for. Water. That simple molecule we drink and bathe in and take for granted can exist in at least 18 different crystalline forms, depending on temperature and pressure. 18 versions of ice, each with different properties, different structures, different rules. We only ever encounter one of them naturally on Earth. The universe uses all of them casually across billions of worlds, creating combinations we're only just beginning to catalog. Gliese 436b taught astronomers something important. It taught them to stop assuming, to stop projecting Earth's conditions onto other worlds, to recognize that chemistry is flexible, that physics allows for arrangements and states we haven't encountered yet, that our intuition shaped by life on a single planet with a narrow range of conditions is a poor guide to what's possible elsewhere. Before Gliese 436b, many scientists believed hot Neptunes should have lost most of their water through evaporation. The heat should have boiled it away, leaving only a rocky core. But Gliese 436b kept its water. It kept it by transforming it, by subjecting it to pressures so intense that the normal rules stopped applying. And in doing so, it expanded our understanding of what planets can be. Now, let's drift in the opposite direction toward the coldest planet we've ever found. If Gliese 436b represents impossible heat trapped in ice, then Ogle 2005 BLG 390LB represents cold so absolute it feels almost philosophical. Discovered in 2006 using a technique called gravitational microlensing, this planet orbits a red dwarf star about 21,500 light-years from Earth, out near the center of our galaxy. It's roughly 5.5 times the mass of Earth, making it one of the smallest exoplanets discovered at the time. And its surface temperature is estimated at around minus 223 degrees Celsius, or minus 370 degrees Fahrenheit. That's only about 50 degrees above absolute zero, the theoretical lowest possible temperature, the point where molecular motion nearly ceases, where atoms themselves begin to slow and settle into their lowest energy states. At those temperatures, chemistry barely happens. Reactions that occur readily on Earth, reactions that sustain life, that drive weather, that shape geology, all of them grind to a halt. Water. If it exists on Ogle 2005 BLG 390LB, would be harder than steel frozen into a solid that would never melt, never thaw. Not even under direct sunlight, if the planet had any to speak of. Gases that make up Earth's atmosphere, nitrogen, oxygen, carbon dioxide, would condense into solids or liquids, forming layers of frozen air on the surface. The planet would be silent, still a frozen tomb, where even the wind has died, where nothing moves, nothing changes, nothing breathes. Scientists suggest that if you could somehow stand on Ogle 2005 BLG 390LB without freezing instantly, you'd see a landscape unlike anything on Earth. No erosion from wind or water, no tectonic activity to crack the surface, just endless plains of ice and rock preserved in a state of near-perfect stasis. Unchanged for billions of years, a world where time itself seems to have stopped. The discovery of Ogle 2005 BLG 390LB was significant for another reason. It proved that small rocky planets, planets that might resemble Earth in size and composition, can exist in the outer reaches of star systems, far beyond the habitable zone where liquid water might exist. For a long time, astronomers focused their search for exoplanets on regions close to stars, where detection was easier, where planets were larger and more massive, where gravitational effects were stronger. But Ogle 2005 BLG 390LB showed that planets exist everywhere, even in the cold, dark outer regions, where sunlight is barely a whisper. These frozen worlds might outnumber the temperate ones. They might be the norm, while planets like Earth bathed in warmth and light are the rare exceptions. That realization is humbling. It suggests that most planets, perhaps the vast majority, are lifeless, not because they lack the right chemistry, but because they're simply too cold too far from the energy they need to kindle complexity. But cold isn't the only extreme. Let's talk about darkness. Pure, absolute, light-devouring darkness. Meet Tauri S2b, discovered in 2006 orbiting a star about 750 light-years away in the constellation Draco. Tauri S2b is a gas giant similar in size to Jupiter, but with one extraordinary property. It reflects less than 1% of the light that hits it. Less than 1%. To put that in perspective, Earth reflects about 30% of the sunlight it receives. Jupiter reflects about 52%. Even charcoal, one of the darkest substances we have on Earth, reflects about 4% of visible light. Tauri S2b is darker than charcoal, darker than coal, darker than anything we've ever created or encountered. It is, as far as we know, the darkest planet in the universe. Why is it so dark? Scientists aren't entirely sure. The leading theory suggests that Tauri S2b's atmosphere contains light-absorbing chemicals, possibly vaporized sodium, potassium, or titanium oxide, which soak up most of the incoming radiation rather than reflecting it. The planet orbits extremely close to its star, completing a full orbit every 2.5 days, which means it's constantly bathed in intense starlight. That light heats the atmosphere to over 1,800 degrees Fahrenheit, hot enough to keep those chemicals in gaseous form, suspended in thick clouds that trap and absorb photons before they can escape. The result is a planet that glows faintly red, not from reflected light, but from its own heat, radiating outward, a dim ember, floating in the blackness, barely visible even to the most sensitive telescopes. Imagine approaching Tauri S2b in a spacecraft. As you get closer, you'd expect to see the planet illuminated by its nearby star, the way we see Venus glowing brightly in our evening sky. But Tauri S2b wouldn't shine. It would be a void, a silhouette, a black sphere against the stars, defined only by the starlight it blocks out. You'd see it not because it reflects light, but because it doesn't, because it's a hole in the sky, an absence where something should be. Some researchers have called it a stealth planet, nearly invisible despite its enormous size. It's the cosmic equivalent of a black hole, not in the gravitational sense, but in the optical one. Light goes in, light doesn't come back out. There's something unsettling about that, isn't there? We rely on light to understand the universe. We use telescopes to gather photons from distant objects, analyzing their wavelengths, their intensity, their spectra, piecing together stories about composition and temperature and motion. But Tauri S2b resists that. It swallows the light. It hides. It reminds us that not everything in the universe wants to be seen, that some worlds are so alien in their properties that even observing them becomes a challenge. And it raises a question. How many other planets like Tauri S2b exist out there too dark to detect, too stealthy to catalog, orbiting their stars in silence unknown and unknowable? What ties these planets together? The burning ice, the frozen wasteland, the darkness absolute, is that they all represent extremes. They exist at the edges of what's possible, pushing against the boundaries of physics and chemistry, showing us that the universe is not a place of gentle gradients and smooth transitions. It's a place of harsh contrasts, a place where water can be solid at temperatures that melt, laid where planets can be colder than anything we've ever experienced, where darkness can be so complete that even starlight cannot escape. These aren't anomalies. These are options, variations on a theme. Different ways matter can arrange itself when left alone to interact with gravity's radiation and time. And each one teaches us something. Gliese 436b teaches us that pressure can overrule temperature, that the phases of matter are more complex than we learned in school. Ogil 2005 BLG 390 et al. B teaches us that cold, true cold can preserve a world. In stasis can silence all chemistry, and motion can create planets that are more like museums than living systems. TRES-2b teaches us that visibility is not guaranteed, that some things in the universe prefer to hide, that darkness can be an active property rather than a passive absence. Together, they expand our sense of what planets can be, how varied they are, how little our experience on Earth prepares us for the full range of possibilities. But extremes of temperature and light are only part of the story. There are planets whose strangeness comes not from their surfaces, but from their motions, from the paths they trace through space, from orbits so chaotic and unlikely that they seem more like accidents than outcomes of natural law. Let's turn our attention there now, to the worlds that move in ways they shouldn't, to the planets whose years are measured not in stable rhythms, but in wild elliptical swings between fire and ice. Picture a world where summer means being close enough to your sun that oceans would boil, and winter means drifting so far away that nitrogen freezes out of the air. A planet whose year isn't a gentle circle, but a violent ellipse swinging between extremes so dramatic that no season lasts long enough for stability, no climate persists long enough for anything to adapt. This is HD 2782b, a gas giant about 117 light-years from Earth, and it has the most eccentric orbit of any exoplanet we've ever discovered. Its path around its star isn't remotely circular. It's stretched elongated, almost comet-like, bringing it as close as 0.2 astronomical units to its sun at one point, and flinging it out to 2.5 astronomical units at another. For perspective, that's the difference between being closer than Mercury and farther than Mars, all within the span of a single orbit that lasts about 597 days. HD 2782b was discovered in 2006 by a team using the radial velocity method, watching its parent star wobble as the planet's gravity tugged it back and forth. At first, the data seem wrong. Orbits that eccentric shouldn't be stable, or at least that's what the model suggested. Planets form from disks of gas and dust that circulate around young stars, and those disks tend to create circular orbits through a process called circularization, where gravitational interactions and tidal forces gradually smooth out any irregularities. Over millions of years, eccentric orbits should settle, should round out, should become predictable. But HD 2782b never got that memo. Its orbit remains wildly elliptical, a cosmic anomaly that forced astronomers to reconsider how planetary systems evolve. What could cause an orbit like this? Scientists suggest several possibilities. Perhaps HD 2782b had a sibling, another massive planet that once shared the same system. The two planets might have engaged in a gravitational dance, pulling and pushing on each other until their orbits became unstable. One planet could have been ejected, entirely flung out into interstellar space, while the other, HD 2782b, was left behind with its orbit severely distorted. Or perhaps a passing star came too close, its gravity stirring the system like a spoon through water, disrupting the careful balance that had existed for millions of years. We see evidence of such encounters in our own solar system. The Oort cloud, that distant shell of icy bodies surrounding the sun, is thought to have been shaped by gravitational perturbations from nearby stars billions of years ago. If it happened here, it can happen anywhere. The implications for any hypothetical moons orbiting HD 2782b are staggering. Imagine living on such a moon, if life could exist there, which it almost certainly couldn't. Your calendar would be chaos. For part of the year, your planet would race toward the sun, heating rapidly, bathing you in light, so intense that it might strip away atmospheres, boil away. Oceans turn rock molten. Then, just as quickly, the planet would swing outward, retreating into the cold and dark temperatures, plummeting any remaining atmosphere, freezing solid, the sun shrinking to a distant point of light, barely distinguishable from other stars. There would be no rhythm, no predictability, no seasons in any meaningful sense. Just extremes, just violence, just the universe demonstrating over and over that stability is not guaranteed, that the paths we trace through space are subject to forces we can neither control nor fully predict. HD 2782b taught us something humbling. It taught us that our solar system, with its neat, nearly circular orbits, with its planets spaced at predictable intervals, following paths that have remained essentially unchanged for billions of years, is not the standard. It's the exception. Most planetary systems we've discovered are messier, more chaotic, more prone to disruption. Planets migrate inward from where they formed. They collide. They eject each other. They settle into resonances, orbital configurations, where their periods form simple ratios 2-to-1, 3-to-2, creating patterns that look orderly, but are actually the result of violent past interactions. Our solar system is calm because it survived, because the disruptions happened early during formation, and everything that was going to be ejected already was. But out there in younger systems, in systems that haven't had time to settle the chaos, is ongoing. Now, let's drift to something even stranger, a planet that orbits not one sun but two. Kepler's 16b, discovered in 2011, became famous almost immediately. Astronomers called it Tatooine, after the fictional desert planet in Star Wars, where Luke Skywalker watched twin suns set over the horizon. But Kepler 16b is real. It's about 245 light-years from Earth, roughly the size of Saturn, orbiting two stars that circle each other every 41 days. The planet itself takes 229 days to complete one orbit around both stars, tracing a wide path through a system where gravity is complicated, where the pull comes from two sources instead of one, where tidal forces tug in multiple directions simultaneously. Binary star systems are common. Astronomers estimate that about half of all stars in our galaxy exist in binary or multiple star systems locked in gravitational embraces with one or more companions. For a long time, scientists weren't sure if planets could form in such systems. The gravitational interactions seemed too complex, too disruptive. Any protoplanetary disk trying to coalesce into planets would be constantly disturbed by the two stars, their orbits stirring the material, preventing it from settling into stable configurations. But Kepler 16b proved that assumption wrong. Planets can form in binary systems. They can survive. They can even thrive in their own strange way. What would it be like to stand on Kepler 16b, assuming you could find solid ground, which you couldn't because it's a gas giant? You'd see two suns in the sky, one slightly larger and brighter than the other, both moving in complex patterns relative to each other and to you. Sometimes they'd rise together. Sometimes one would rise while the other set. Sometimes they could eclipse each other, one star passing in front of the other, dimming the light, casting strange double shadows across the landscape. Your sense of time would be fundamentally different from ours. Days and nights wouldn't follow the simple rhythm we're used to. They'd overlap, interfere, create periods of dim twilight when both stars are low on the horizon, and periods of intense brightness when both are overhead. Scientists suggest that if Kepler 16b had a moon, and if that moon had an atmosphere and liquid water, which is a lot of ifs, the climate on that moon would be extraordinarily complex, driven by two heat sources instead of one, creating weather patterns we can barely begin to model. Kepler 16b isn't alone. We've found dozens of circumbinary planets, worlds that orbit binary star systems, each one adding to our understanding of how planets form and survive in gravitationally complex environments. Some orbit close to their stars, completing orbits in just a few days. Others orbit far out, taking years. Some systems have multiple planets all circling the same binary pair, somehow maintaining stable orbits despite the gravitational chaos. These discoveries challenge the idea that planetary formation requires calm, stable conditions. They suggest that planets are resilient, adaptable, capable of forming in almost any environment where there's enough material to work with. But if binary stars seem strange, let me introduce you to something stranger still: a planet orbiting a dead star. PSR B57 plus Scarang 12. Discovered in 1992, was actually the first confirmed exoplanet system ever detected, predating the discovery of 51 Pegasi b by 3 years. But it didn't orbit a normal star. It orbited a pulsar, the collapsed remnant of a massive star that exploded in a supernova millions of years ago. Pulsars are neutron stars objects so dense that a teaspoon of their material would weigh about 1 billion tons. They spin incredibly fast, sometimes hundreds of times per second, and they emit beams of radiation from their magnetic poles. As they spin, those beams sweep across space like lighthouse beacons. And if Earth happens to be in the path of one of those beams, we detect regular pulses of radio waves, hence the name. Astronomer Alexander Volshan discovered PSR B57 plus 12's planets not by watching the pulsar wobble, but by noticing tiny irregularities in the timing of its pulses. The planets, 3 of them, were tugging on the pulsar as they orbited, causing it to shift position ever so slightly, which in turn caused the pulses to arrive at Earth a fraction of a second early or late. By analyzing those timing variations, Volshan could calculate the masses and orbits of the planets with extraordinary precision. 2 of them are several times more massive than Earth. The third is smaller, roughly the size of our moon. All of them orbit close to the pulsar well, within the distance of Mercury's orbit around our sun. Here's the puzzle. How did these planets get there? Pulsars form from supernovae explosions, so violent they can outshine entire galaxies for a brief moment. Any planets that existed around the star before it exploded should have been vaporized, destroyed, blown away into space by the force of the blast. The radiation alone would have been enough to sterilize anything nearby. So, these planets, the ones orbiting PSR B125E7 plus 12, now must have formed after the supernova. Scientists suggest they coalesced from the debris left behind from the ashes of the dead star, from material that settled into a disk around the pulsar and gradually accumulated into planetary bodies. In a sense, these are second-generation planets born from death, formed in the wreckage of a catastrophe orbiting a corpse. The environment around a pulsar is hostile beyond comprehension. The radiation is intense, a constant stream of high-energy particles and electromagnetic waves that would strip away any atmosphere, sterilize any surface, make life, as we know it, utterly impossible. The magnetic fields are trillions of times stronger than Earth's, strong enough to warp the very structure of atoms. And yet, planets exist there. They orbit. They persist. They remind us that planetary formation isn't a fragile process that only happens under ideal conditions. It's a robust process, one that occurs wherever there's gravity, material, and time, even in the most extreme environments imaginable. What strikes me about these orbital oddities, the eccentric paths, the binary systems, the pulsar planets, is how they dismantle our assumptions. We thought orbits should be circular. We thought planets needed stable single stars. We thought supernova explosions would destroy everything nearby. But the universe doesn't care about what we think should happen. It operates according to physics, not our preferences. And physics allows for possibilities we never imagined. Every strange orbit we discover, every impossible configuration, expands the space of what's possible, forces us to revise our models, challenges us to think more broadly about how planetary systems form, evolve, and endure. And it raises a question worth considering. If orbits can be this chaotic, this unpredictable, this variable, what does that mean for the search for life? Stability matters for biology. Life needs time to evolve, time to adapt, time to build complexity. a planet swinging wildly between hot and cold, bathed in radiation from two suns or a dead star, never settling into a predictable rhythm, doesn't offer that time. It offers only chaos, only extremes, only conditions that shift faster than evolution can respond. Maybe that's why Earth's stable, nearly circular orbit matters so much. Maybe that's why the calm we take for granted is actually one of the prerequisites for our existence. But not all strangeness comes from motion. Some planets are strange simply because of what they're made of, because of their size and density, because they exist when theory says they shouldn't. Let's turn our attention now to the giants that defy the laws of planetary formation, the inflated worlds and massive anomalies that have astronomers questioning everything they thought they understood. There's a planet out there with a density of styrofoam, not similar to styrofoam, not reminiscent of it, actually less dense than styrofoam, lighter than cork, so puffy and inflated that if you could somehow find an ocean large enough, this gas giant would float. TAR-ES 4b, discovered in 2007, is one of the largest exoplanets ever found, with a radius 1.7 times that of Jupiter, yet its mass is only about 0.84 times Jupiter's. Do the math, and you get a density of roughly 0.2 grams per cubic centimeter. For comparison, Jupiter's density is 1.3 grams per cubic centimeter. Saturn, the least dense planet in our solar system, clocks in at 0.7. Water is 1.0. Balsa wood, one of the lightest natural materials on Earth, is about 0.16. TAR-ES 4b is barely denser than balsa. It's a world the size of a small star, but with less substance than you'd expect from a cosmic soap bubble. TAR-ES 4b orbits a star about 1/400 light-years from Earth in the constellation Hercules. It completes one orbit every 3.55 days, which places it dangerously close to its parent star, close enough that the intense radiation heats its atmosphere to over 2,300 degrees Fahrenheit. And this is where things get puzzling. According to our models of planetary formation and evolution, hot Jupiters like TAR-ES 4b should be contracting, not expanding. When gas giants form, they start out large and gradually cool over billions of years, their atmospheres condensing, their radii shrinking. Jupiter itself is still slowly contracting, releasing heat left over from its formation, getting imperceptibly smaller with each passing millennium. But TAR-ES 4b isn't contracting. It's inflated, bloated, as if something is pumping energy into its atmosphere, keeping it hot and expanded despite the relentless pull of gravity trying to compress it. Scientists suggest several possible mechanisms. The most popular theory involves tidal heating. TAR-ES 4b's orbit might not be perfectly circular, and if it's even slightly elliptical, the gravitational pull from its star would vary throughout the orbit, stretching and squeezing the planet in a rhythmic cycle. That flexing generates heat, the same way bending a paperclip back and forth makes it warm. On a planetary scale, with a gas giant being kneaded by stellar gravity billions of times over millions of years, that heat adds up. It keeps the atmosphere hot, keeps the molecules moving fast, keeps the planet puffed up like a balloon someone keeps blowing into. Another possibility involves atmospheric circulation. If the planet's winds are strong enough, they might transport heat from the day side to the night side so efficiently that the entire atmosphere stays uniformly hot, preventing any part of it from cooling and contracting. Or perhaps the star's intense radiation is being absorbed deep in the planet's atmosphere, in layers where molecular hydrogen breaks apart into individual atoms, a process that requires energy and generates heat, creating an internal furnace that counteracts gravitational compression. The truth is, we're not entirely sure why TAR-ES 4b is so inflated. And that uncertainty bothers astronomers because it suggests there's something fundamental we're missing about how giant planets behave when subjected to extreme stellar radiation. TAR-ES 4b isn't unique. We've found dozens of other inflated hot Jupiters, each one larger than it should be, each one defying our models in slightly different ways. Some, are even puffier than TRES 4b. WASP 17b, for instance, has a radius twice that of Jupiter, but only half the mass, giving it an absurdly low density of about 0. 13 grams per cubic centimeter, less dense than balsa wood, less dense than aerogel, one of the lightest solid materials we've ever created. If you could stand on WASP 17b, which you couldn't because it's a gas giant with no surface, you'd weigh almost nothing. Gravity would barely hold you down. You could probably jump hundreds of meters into the air if there was air to jump through, and if you weren't instantly vaporized by the heat. These inflated planets challenge our understanding of planetary physics in fundamental ways. They suggest that the relationship between mass radius and temperature is more complicated than we thought. They hint at processes we haven't accounted for, energy sources we haven't identified, mechanisms that operate at scales and in conditions we've never encountered. And they remind us once again that the universe is under no obligation to conform to our equations. We build models, we make predictions, and then reality presents us with a planet less dense than wood, floating impossibly in space, daring us to explain it. Now, let's shift to the opposite extreme. Not planets that are too large, but planets that are too massive, too heavy, existing in places they shouldn't. HATE P32b, discovered in 2011, is a perfect example. It's about 2.04 times the mass of Jupiter, making it one of the more massive gas giants we've found. But here's the problem. It orbits its star at a distance of only 0.0344 astronomical units. To put that in perspective, Mercury orbits the Sun at 0.39 AU. HATE P32b is almost 12 times closer to its star than Mercury is to ours. At that distance, the stellar radiation is intense enough to boil away atmospheres, to strip planets down to their cores, to make the existence of a massive gas giant not just unlikely, but seemingly impossible. According to planetary formation theory, gas giants form far from their stars, out in the cold regions beyond what we call the frost line, the boundary, where temperatures are low enough for volatile compounds like water, methane, and ammonia to freeze into solid ice. Those ices act as building blocks, accumulating into planetary cores massive enough to gravitationally capture huge envelopes of hydrogen and helium gas from the surrounding protoplanetary disk. That's how Jupiter and Saturn formed. They started as icy cores in the outer solar system, then grew into gas giants by accreting material over millions of years. But HAT P32b isn't in the outer reaches of its star system. It's practically skimming the star's surface. So, how did it get there? The leading explanation is planetary migration. Scientists suggest that HAT P32b formed much farther out where it was cold enough for ice to exist and gas to accumulate. Then over time, interactions with the protoplanetary disk or with other planets caused it to spiral inward, migrating toward its star until it reached its current position. Migration isn't rare. We see evidence of it throughout the galaxy. Many hot Jupiters likely started their lives in the outer parts of their systems before moving inward. But HATE P32b is unusual because it managed to migrate so close without losing its atmosphere. At that distance, the star's radiation should be stripping away the planet's outer layers, eroding it, turning it into a smaller, denser body. Yet, HATE P32b remains massive intact, defiantly clinging to its gas envelope despite the hostile conditions. Some researchers have proposed that HAT P32b might be relatively young, that it hasn't been in its current orbit long enough for significant atmospheric erosion to occur. Others suggest that the planet's strong magnetic field might be protecting it, deflecting the stellar wind, creating a magnetosphere that shields the upper atmosphere from being blown away. Or perhaps there's a mechanism we haven't discovered, yet some process that allows gas giants to retain their mass even under extreme radiation. Some balance between loss and retention that our models don't account for. Whatever the explanation, HATE P32b is. A puzzle, a planet that exists where it shouldn't, in a configuration that challenges our understanding of how planetary systems evolve. And then there are the planets that shouldn't exist for an entirely different reason. Not because they were in the wrong place, but because the stars they orbit shouldn't have planets at all. Consider the metal-poor stars, ancient stars that formed in the early universe when heavy elements were scarce. In the first few 100 million years after the Big Bang, the universe contained mostly hydrogen and helium, the lightest elements created during the initial moments of cosmic expansion. Heavier elements, carbon, oxygen, silicon, iron, all the stuff that makes up rocky planets, and incidentally us, didn't exist yet. Those elements are forged inside stars through nuclear fusion and scattered into space when those stars explode as supernovae. It takes generations of stars, each one creating heavy elements and distributing them through the galaxy to enrich the interstellar medium enough for rocky planets to form. So, logically, stars that formed early before many generations of supernovae had occurred should be metal poor, lacking the heavy elements needed to build planets. And for a long time, that's what astronomers believed. Metal poor stars might have gas giants, maybe, since those are mostly hydrogen and helium, but they shouldn't have rocky planets. There simply wouldn't be enough material. But then, we found planets around metal poor stars anyway. Ship 111952. A star with only 7% of the Sun's metal content has 2 planets. Captain star, estimated to be about 11 billion years old and extremely metal poor, has at least 1 confirmed planet and possibly 2. These discoveries shook the field. They suggested that planet formation might be more flexible, more resourceful, more capable of working with limited materials than we ever imagined. How do you build a planet when there's almost nothing to build, but scientists aren't entirely sure? Perhaps these planets formed from the tiny amount of heavy elements that did exist accumulating material so efficiently that they managed to create planetary cores despite the scarcity. Perhaps the protoplanetary disks around these metal-poor stars were larger or denser than average, compensating for the low metallicity with sheer volume. Or perhaps planet formation can proceed through mechanisms we haven't identified, yet pathways that don't rely as heavily on heavy elements, processes that operate in conditions we thought were too hostile for planetary birth. The existence of these planets is a reminder that nature is creative, that it finds ways to build complexity even when the ingredients are sparse, even when the conditions seem prohibitive. There's a pattern emerging here, isn't there? Across all these strange worlds, the inflated giants, the massive migrants, the planets around metal-poor stars, the common thread is defiance. These planets defy our models. They defy our predictions. They exist in configurations we said were impossible, in places we said were too hostile with properties. We said were unstable. And every time we discover one, we're forced to expand our theories, to add complexity to our equations, to acknowledge that the universe is more inventive than we are. We set rules based on what we observe in our own solar system, and the universe promptly breaks them, showing us that our little corner of space is not representative, that the diversity out there exceeds anything we could have imagined, when all we had to study were 8 planets orbiting 1 star. Do you ever wonder how many other rules we've gotten wrong? How many other assumptions we're making based on limited data that will collapse the moment we find the next impossible planet? Astronomy is in many ways the science of being wrong and then being less wrong. Each discovery doesn't necessarily bring us closer to the truth. It just shows us how much farther the truth extends beyond our current understanding. And that's humbling. It's uncomfortable. But it's also beautiful in a way. It means there's always more to learn, always more to discover, always more strangeness waiting out there in the dark, ready to surprise us. The giants that shouldn't exist are teaching us that existence doesn't require permission. Planets form where they cannot, where we think they should. They persist under conditions we thought were lethal. They thrive in environments we declared impossible. And in doing so, they expand the boundaries of what's possible, not just for planets, but for us, for our imaginations. for our understanding of how creation works when left to its own devices across billions of years and trillions of miles. But size and mass are only part of the equation. There are planets whose age defies belief, worlds that have been circling their stars since the universe was barely a billion years old, carrying memories of a cosmos we can only glimpse through mathematics and light. Let's move through time now backward toward the ancient ones, the planets that remember what the universe was like before Earth even existed. Imagine a world that has been orbiting its star since before our sun existed, before Earth condensed from dust, before the Milky Way looked anything like it does now. A planet so ancient that, when it formed the universe itself, was barely 1 billion years old, still young, still hot, still glowing with the afterglow of creation. This planet exists. It's called PSR BUN 1620-26b, though most astronomers know it by a simpler name, Methuselah, after the biblical figure said to have lived 969 years. But Methuselah the planet makes Methuselah the man look like a newborn. This planet is approximately 12.7 billion years old, nearly 3 times the age of Earth, older than most stars in our galaxy. A survivor from an era of the cosmos we can barely comprehend. PSR B1620-26b orbits in a globular cluster called M4, about 12,400 light-years from Earth in the constellation Scorpius. Globular clusters are ancient stellar cities, dense collections of hundreds of thousands of stars, all born around the same time in the early universe, all gravitationally bound together in a spherical swarm. M4 is one of the oldest clusters we know, and most of its stars are metal-poor, formed before supernovae had enriched the galaxy with heavy elements. According to everything we thought we knew about planet formation, planets shouldn't exist in globular clusters. The environment is too chaotic, too crowded, too metal-poor. Gravitational interactions between stars should disrupt planetary orbits. The lack of heavy elements should prevent rocky cores from forming. And yet, there it is. Methuselah. Defiant. Ancient. Impossible. The planet was discovered in 2003 using the Hubble Space Telescope, though its existence had been suspected for years based on timing irregularities in the pulsar's radio signals. Yes, this ancient planet orbits a pulsar just like the system we discussed earlier, but with a twist. Methuselah orbits both the pulsar and a white dwarf star in a complex triple system, taking about 100 years to complete one orbit around the pair. The pulsar itself is the remnant of a massive star that exploded billions of years ago. The white dwarf is the dense core of a star that exhausted its nuclear fuel and gently shed its outer layers. And somehow, through all the violence, through supernovae and stellar evolution and gravitational chaos, the planet survived. How scientists aren't entirely sure. The leading theory suggests that Methuselah didn't form around the pulsar or the white dwarf. It likely formed around a normal star early in the cluster's history, then was captured by the binary system through a close gravitational encounter. Imagine 3 stars passing near each other in the crowded heart of the globular cluster. One star has a planet. During the encounter, the gravitational dance becomes so complex that the planet's original host star is ejected, flung away into space, while the planet itself is captured by the other 2 stars, now bound to them in a new unstable orbit. Over millions of years, that orbit gradually stabilizes, settling into the configuration we observe today. It's a cosmic adoption story, a planet orphaned by gravitational violence and taken in by a pair of stellar remnants. What makes Methuselah truly remarkable isn't just its age, but what that age implies. When this planet formed roughly 12.7 billion years ago, the universe was radically different. Galaxies were smaller, less structured, still in the process of merging and colliding. The cosmic microwave background radiation, the afterglow of the Big Bang, was about 1,000 times more intense than it is now. Most of the stars in the universe were first-generation stars, massive and short-lived, composed almost entirely of hydrogen and helium. Heavy elements like carbon, oxygen, and iron existed in only trace amounts created in the cores of the very first supernovae and scattered sparingly through space. The universe was in a very real sense chemically primitive. And yet, in that primitive universe, planets formed. Methuselah is proof. It suggests that planet formation began much earlier than we thought, that the process doesn't require a universe rich in heavy elements, that rocky cores and gas giants can coalesce even when the raw materials are scarce. Before we discovered Methuselah, many astronomers believed that planets like Earth couldn't have formed until the universe was at least several billion years old, after enough generations of stars had lived and died to enrich the interstellar medium with the elements needed for rocky worlds. Methuselah forced us to reconsider. It showed us that the universe was building planets when it was still in its infancy, experimenting with planetary systems long before our solar system was even a possibility. Think about the implications. If planets formed that early, could life have emerged that early too? Could there be civilizations out there orbiting ancient stars with billions of years, more evolutionary history than we have? We often talk about the search for extraterrestrial intelligence as if we're looking for our peer species roughly as advanced as we are, give or take a few thousand years. But if life arose on a planet like Methuselah, even just a billion years before it arose on Earth, that civilization would have had an enormous head start. They could be so far beyond us technologically, culturally, philosophically, that we wouldn't even recognize them as life. They might have transcended biology. They might have spread across entire galaxies. They might look at us the way we look at bacteria, interesting in an academic sense, but not really worth engaging with. Or maybe they're gone. Maybe they rose, flourished, and fell billions of years ago, leaving nothing behind but ruins. We'll never find stories we'll never hear. Methuselah makes you think about time in uncomfortable ways. It's been orbiting for longer than Earth has existed. It's witnessed the birth and death of countless stars. It's seen galaxies collide, watched the universe expand, felt the pull of gravity from objects that no longer exist. If that planet could remember, what would it remember? What events has it survived? What catastrophes has it endured? We think of planets as eternal, unchanging, but they're not. They're just slow. They erode, they migrate, they collide, they're ejected. They fall into their stars. But Methuselah has endured 12.7 billion years of existence, and it's still there, still orbiting, still defying the odds. Now let's visit another ancient world, though one with a very different story. TOI 561b, discovered in 2021, is one of the oldest rocky planets we've ever found, estimated to be around 10 billion years old. It's about 1.5 times the mass of Earth and orbits a star called TOI 561, an orange dwarf located about 280 light-years away. What makes this planet particularly interesting isn't just its age, but its composition. Spectroscopic analysis of the host star reveals that it's extremely metal-poor, containing only about 1/4 the heavy element abundance of our Sun. And since planets generally have similar compositions to the stars they form around TOI 561b, is likely metal-poor as well, meaning it's made mostly of lighter elements like silicon and magnesium, with very little iron, nickel, or other heavy metals. On Earth, iron makes up about 32% of our planet's mass, mostly concentrated in the core. Iron is what gives Earth its magnetic field, which shields us from harmful solar radiation and helps retain our atmosphere. Iron is also dense, contributing significantly to Earth's overall density. But TOI 561b, with its low metal content, is probably much less dense than Earth, despite being more massive. Scientists suggest the planet might have a rocky composition, dominated by lighter minerals, giving it a density closer to that of a very large asteroid than a typical rocky planet. It's a fundamentally different kind of world, built from a fundamentally different set of ingredients, a glimpse into what rocky planets looked like in the early universe before supernovae had seeded the galaxy with the full periodic table. TOI 561b orbits extremely close to its star, completing a full orbit in less than 11 hours. 11 hours, that's shorter than a workday. The planet is tidally locked one side, perpetually facing the star, baked to temperatures exceeding 3,000 degrees Fahrenheit, hot enough to vaporize rock. It's not habitable. It's barely even planetary. In the traditional sense, more of a molten ball of lighter elements being slowly eroded by stellar radiation. But its existence tells us something crucial. It tells us that rocky planets, the kind that could potentially support life, have been forming for most of the universe's history. 10 billion years is a long time, long enough for countless generations of life to arise, evolve, and vanish. Long enough for entire ecosystems to flourish and collapse, for civilizations to build and crumble, for the cosmos to experiment with biology in ways we've never imagined. And here's the uncomfortable part. If rocky planets have been around for 10 billion years, and if life arises readily on planets with the right conditions, then where is everyone? This is the Fermi paradox in its starkest form. The universe is old, planets are common. Many of those planets are ancient. If life and intelligence are natural outcomes of planetary evolution, the galaxy should be teeming with civilizations, many of them far older and more advanced than ours. We should see evidence everywhere: megastructures, radio signals, terraformed worlds, something. But we don't. We see silence, emptiness, a cosmos that seems, for all its vastness and age, strangely devoid of voices other than our own. Maybe life is rarer than we think. Maybe the conditions that led to us, the specific sequence of events, the narrow windows of stability, the unlikely accidents are so improbable that even across billions of planets and billions of years, intelligence arises only a handful of times. Maybe we're genuinely alone or nearly so isolated by incomprehensible distances and the sheer statistical improbability of conscious thought. Or maybe life is common, but intelligence is fragile. Maybe every civilization that reaches our level of technology eventually destroys itself through war or environmental collapse or some other catastrophe we haven't encountered yet. Maybe the silence we hear isn't the absence of life, but the echo of countless failed experiment species that rose and fell before they could reach the stars. Or maybe we're simply looking in the wrong way. Maybe advanced civilizations don't broadcast radio signals. Maybe they don't build megastructures. Maybe they've found forms of existence we can't detect, encoded themselves into quantum states, uploaded their consciousness into simulations, transcended physical form entirely. If we're looking for signs of technology comparable to ours, we might be looking for the wrong thing, searching for industrial-age signatures in a post-biological universe. It's like trying to find evidence of modern civilization by listening for smoke signals. We're using the tools we have, asking the questions we know how to ask, but the answers might exist in forms we haven't conceived of yet. The ancient planets Methuselah and TOI 561b and others like them force us to confront these questions. They've been here so much longer than we have. They've orbited through epochs we can only study through cosmology and mathematics. They've seen the universe change, watched galaxies evolve, felt the slow cooling of cosmic expansion. And through it all, as far as we can tell, they've remained silent, lifeless, barren, just rock and gas and gravity obeying the laws of physics, without comment, without awareness, without meaning. But maybe that's not sad. Maybe that's just honest. The universe doesn't owe us company. It doesn't owe us answers. It's under no obligation to be inhabited, to be full of voices and stories and intelligences eager to meet us. It simply is. Vast and ancient and mostly empty, with pockets of complexity scattered across incomprehensible distances, each one isolated, each one temporary, each one a brief experiment in organization against entropy. And if we're alone, if we're the only ones asking these questions, looking up at the stars and wondering, then maybe that makes our existence more precious, not less. Maybe being rare, being unlikely, being the universe's way of knowing itself in this particular corner of space and time is enough. The ancient planets remind us that time is long, longer than civilizations, longer than species, longer than continents or oceans or atmospheres. Planets endure, they orbit, they witness. And maybe that's all they do. Maybe we're the ones who bring meaning, who look at these ancient worlds and feel wonder, who assign names and tell stories and calculate ages and dream about what could have been, what might still be, what we ourselves might become if we survive long enough. But age is only one measure of strangeness. There are planets whose composition defies comprehension, worlds made of materials we consider precious, covered in oceans, deeper than any canyon, wrapped in atmospheres that rain molten rock. Let's drift toward those places now, toward the water worlds and diamond hearts where matter arranges itself in forms that seem more like fantasy than physics. There's a planet 48 light years from Earth where the ocean is so deep that if you could somehow sink to the bottom, the pressure would be millions of times greater than anything we experience in our deepest trenches. The water wouldn't be liquid anymore. It would transition through exotic forms of ice we've never encountered on Earth, crystalline structures that exist only under crushing gravitational force, until finally, somewhere far below, you'd reach a core of compressed rock so hot and dense, it might as well be another world entirely. This is GJ1214b, discovered in 2009, and scientists suggest it might be entirely covered in water. A true ocean planet with no land, no continents, no surface to speak of, just water all the way down for hundreds, possibly thousands of miles. GJ1214b orbits a red dwarf star in the constellation Ophiuchus, completing one orbit every 1.6 Earth days. It's roughly 2.7 times Earth's diameter and about 6.5 times Earth's mass, placing it in a category we call super-Earth's planets, larger than our own, but smaller than Neptune. When astronomers first measured its density, they found something surprising. GJ1214b is too light to be made entirely of rock and metal, but too heavy to be a gas giant. The only explanation that fits the data is that a significant portion of its mass, perhaps 25% or more, is water, not surface water, not oceans like Earth's, which make up less than 0.1% of our planet's total mass. We're talking about a world where water is a primary structural component, where the planet itself is built from H2O in various forms, liquid ice, vapor, exotic, high-pressure phases. We don't have names for it yet. Imagine what such a world would look like if you could observe it up close. The surface, if you can call it a surface, would be an endless expanse of ocean stretching in all directions under a thick, steamy atmosphere, rich in water, vapor, and hydrogen. There would be no islands, no continents, no relief from the monotony of waves. The sky would be hazy, perpetually clouded, the star above dimmed to a diffuse glow by layers of atmospheric moisture. And beneath the waves, the ocean would deepen beyond comprehension. On Earth, our oceans average about 2.3 miles deep, with the deepest point, the Mariana Trench, reaching just under 7 miles. But GJ1214b's ocean might be hundreds of miles deep, transitioning through multiple pressure regimes as you descend. Near the surface, water behaves as it does on Earth, liquid and familiar. But deeper down, the pressure increases. At a certain depth, the water would become so compressed that it transitions into a phase called Ice 7, a crystalline form of ice that remains solid even at temperatures exceeding 200 degrees Fahrenheit. Go deeper still, and you might encounter Ice 10, the same exotic phase we discussed on Gliese 436b, where molecular structure changes under pressure so extreme that the material barely resembles water anymore. Scientists suggest that at the very bottom of this global ocean, beneath miles of exotic ice layers, there might be a rocky core, the original planetary seed, around which all this water accumulated during formation. But you could never reach it. The pressure would crush any probe, any vessel, any material we know how to create. The temperature would climb into the thousands of degrees. The ice above would be harder than steel. denser than diamond, immovable and eternal. It's an ocean, yes, but also a prison, sealing away whatever lies beneath, in layers of frozen water that will never melt, never yield, never allow passage. What would it be like to live on a water world, like GJ 1214b? Could life exist there? Possibly, though, it would be nothing like life on Earth. There's no land for plants to root and no dry surface for animals to walk on. No shallow zones where sunlight can penetrate and drive photosynthesis. Any life that arose on such a planet would have to be entirely aquatic, drifting through the ocean layers, perhaps feeding on chemical energy from hydrothermal vents on the rocky core far below, or harvesting energy from the dim starlight filtering through the atmosphere. It would be a dark, slow existence life, clinging to whatever resources are available in an environment that offers almost no variation, no seasons, no geographical diversity. Just depth and pressure and the slow circulation of water that has nowhere to drain. And GJ 1214b isn't alone. We've found several other candidates for ocean planets, worlds with densities and compositions suggesting they're rich in water. Kepler 22b, discovered in 2011, orbits within its star's habitable zone and might be a water world with a global ocean beneath a thick atmosphere. Kepler 62e and Kepler 62f, both discovered in 2013, are super-Earths that could be entirely ocean-covered, though we can't say for certain without more detailed observations. The prevalence of these water worlds suggests that planets rich in H2O are not rare. They might be common, possibly more common than rocky planets like Earth. If that's true, it means most habitable zone planets, most worlds that exist at the right distance from their stars for liquid water to exist, might be drowning in it, covered entirely with no land to offer refuge, no continents for civilizations to build on. It makes you appreciate Earth's geography, doesn't it? We have oceans, yes, covering about 70% of our surface. But we also have land. We have mountains and valleys, deserts and forests, ice caps and plains. We have diversity variation environments that range from the driest deserts to the deepest trenches, from tropical rainforests to frozen tundra. That diversity matters. It drives evolution. It creates niches. It allows for specialization, adaptation, complexity. A water world, for all its oceans, might be biologically poorer than Earth, not because water is a bad medium for life, but because uniformity limits the possibilities. When every environment is essentially the same, when there's no variation in altitude or temperature or substrate, evolution has fewer directions to explore. Now, let's shift from water to carbon, from the mundane to the absurd. Meet 55 Cancri, a planet orbiting a star about 40 light-years away in the constellation Cancer. This planet is roughly twice Earth's diameter and about 8 times Earth's mass, making it a super-Earth. But what makes 55 Cancri truly extraordinary isn't its size, it's its composition. Scientists suggest that this planet might have a core made largely of diamond, not diamond deposits, not diamond veins. A diamond core potentially thousands of miles thick crystalline carbon compressed by gravity into the hardest natural material in the universe. How is that possible? It comes down to chemistry and pressure. 55. Cancri E orbits very close to its star, so close that it completes a full orbit in just 18 hours. The surface temperature exceeds 3,900 degrees Fahrenheit, hot enough to melt most metals. The planet is tidally locked one side, perpetually facing the star the other, in eternal darkness. Spectroscopic analysis of the host star reveals that it's unusually rich in carbon relative to oxygen, and planets typically have similar compositions to their parent stars. On Earth and on most rocky planets, oxygen is more abundant than carbon, which means that carbon bonds with oxygen to form carbon dioxide and carbon monoxide, leaving little free carbon to crystallize. But on a carbon-rich planet like 55 Cancri E, there's more carbon than oxygen can bond with, leaving large amounts of free carbon to exist in its elemental form. Under the extreme pressures inside the planet, that carbon crystallizes into diamond, forming a core that might contain more diamond than exists in all of Earth's crust, mantle, and core combined. Imagine that. A planet with a heart of diamond glittering in the darkness of its interior, unseen, untouchable, worth more than all the wealth humanity has ever accumulated, yet utterly useless because it's unreachable, locked away by gravity and heat, and the sheer inhospitality of the environment above it. On Earth, diamonds are valuable because they're rare, because we've assigned them cultural and economic significance because they're beautiful and difficult to obtain. But on 55 Cancri E, diamond isn't rare. It's common. It's just geology. It's the way carbon behaves under pressure, no more special than granite or basalt. The universe doesn't care about our values, our economics, our aesthetics. It arranges matter according to physics, and sometimes that arrangement happens to produce things we find precious. Scientists have also suggested that 55 Cancri E's surface might be covered in a layer of graphite, another form of carbon, which would make the planet appear black and reflective, like a polished coal sphere orbiting its star. The atmosphere, if it exists, might contain silicon carbide and other carbon compounds, creating a hazy envelope that scatters light in strange ways. And beneath that, beneath the graphite crust and the layers of compressed carbon compounds, lies the diamond core, forever hidden, forever inaccessible, a treasure vault no one will ever open. But diamonds aren't the strangest thing we found. Let's talk about K2-141b, a planet so extreme that it rains rocks. Discovered in 2018, K2-141b is a super-Earth orbiting a star about 202 light-years away. It's tidally locked with a dayside that reaches temperatures exceeding 400 degrees Fahrenheit. At those temperatures, rock doesn't just melt, it vaporizes. Sodium silicon monoxide, silicon dioxide, all of them exist as gases in the atmosphere rising on thermal currents from the molten surface. These gaseous rock particles are carried by supersonic winds toward the night side, where temperatures drop low enough for them to condense, and then they fall, as rain. Molten droplets of rock glowing orange and red, plummeting through the darkness, splattering against the frozen surface below. Scientists suggest that K2-141b has a weather cycle similar to Earth's water cycle, but made of rock instead of H2O. On the day side, the surface is an ocean of lava, vast and churning, heated by the relentless radiation from the nearby star. Rock evaporates from this magma ocean, rising into the atmosphere, forming clouds of vaporized minerals. Winds carry these clouds toward the night side, where they cool, condense, and precipitate as rain. The rain collects on the surface, forming flows of molten lava that eventually make their way back toward the day side, where the cycle begins again. It's weather, but alien, hostile, operating on principles we recognize, but with materials we'd never associate with meteorology. What would it be like to stand on K2-141b's night side during a rock rainstorm? You'd see the sky filled with glowing droplets, thousands of them, each one a tiny sphere of molten silicon dioxide falling at terminal velocity, bright against the darkness. You'd hear them impact a constant pattering, hissing as they strike the frozen rock surface and begin to cool and solidify. The ground beneath your feet would be slick with fresh lava, still warm, still soft, gradually hardening as the heat dissipates into the frigid air. And if you look toward the Terminator, the boundary between day and night, you'd see a faint glow on the horizon, the edge of the lava ocean, a sea of fire just beyond the rim of perception, unreachable, eternal, the source of the rain that falls endlessly through the dark. These exotic worlds, the endless oceans, the diamond cores, the molten rock rain, they all share a common thread. They're places where familiar materials behave in unfamiliar ways, where the elements we take for granted, water, carbon, silicon, are subjected to conditions so extreme that they transform, rearrange, become something strange and wonderful and terrifying. On Earth, water is gentle, Carbon is coal or diamond, solid and stable. Rocks are the ground beneath our feet, permanent and unchanging. But elsewhere in the vast laboratory of the universe, water becomes exotic. Ice carbon becomes planetary cores. Rock becomes weather. The rules don't change. Physics is constant. But the outcomes vary wildly depending on temperature, pressure, composition, proximity to stars. And that variety, that diversity of planetary environments, expands our sense of what's possible. It shows us that planets aren't just different in size or distance from their stars. They're different in fundamental ways, built from different materials, governed by different dominant processes, hosting phenomena we never imagined until we looked closely enough to see them. Every new exoplanet we discover adds another data point, another example, another variation on the theme of what a world can be. And collectively, those data points are teaching us that the universe is far more creative than we are, that it explores possibilities we haven't thought of yet, that the range of planetary types vastly exceeds the handful of examples we have in our own solar system. But not all planets have the comfort of a star to orbit. There are worlds adrift in the darkness, wandering alone through the void, with no sun to warm them, no light to guide them, exiled from the gravitational embrace of stellar systems. Let's follow them now, out into the cold, into the silence, into the endless night where rogue planets wander without destination, without hope, without end. Picture a planet drifting through the darkness between stars, untethered from any sun, moving through space alone. No dawn ever breaks on its surface. No sunset colors its sky. There are no seasons, no cycles, no rhythms tied to stellar orbits. Just silence, just cold, just the faint distant glow of galaxies too far away to offer warmth or light or companionship. This isn't science fiction. These planets exist. We call them rogue planets, orphan worlds, nomads of the cosmos. And there might be billions of them wandering through our galaxy right now, invisible, undetected, drifting through the void, with no destination, no home, no star to call their own. CFBDSIR 2149-0403 was one of the first rogue planets we confirmed, discovered in 2012, floating freely through space about 130 light-years from Earth. It's roughly 4 to 7 times the mass of Jupiter, and it's alone, completely alone. No star nearby, no planetary siblings, no gravitational anchor holding it in place. Just a massive ball of gas and dust, cooling slowly in the darkness, moving through interstellar space at tens of kilometers per second, following a trajectory determined by whatever violent event ejected it from its original star system millions or billions of years ago. When astronomers first detected it, they weren't sure what they were looking at. It emitted a faint infrared glow heat left over from its formation, but there was no nearby star to explain its presence. It took careful analysis measuring its temperature, its spectrum, its motion, to confirm that this was indeed a planet, not a failed star or a brown dwarf, but a genuine planetary body adrift in the cosmic ocean. How does a planet become rogue? How does a world that once orbited a star end up cast into the darkness? Scientists suggest several mechanisms. The most common involves gravitational interactions during the chaotic early stages of planetary system formation. Imagine a young star system still forming with multiple large planets orbiting at varying distances. Their gravitational fields interact, pulling and pushing on each other in complex ways. Over millions of years, these interactions can destabilize orbits, causing planets to migrate inward or outward, sometimes crossing paths with each other. When two massive planets have a close encounter, their mutual gravity can slingshot one of them out of the system, entirely accelerating it to escape velocity, flinging it into interstellar space like a stone from a catapult. The ejected planet carries its orbital velocity with it, modified by the gravitational interaction, and continues moving through the galaxy alone, forever separated from the star it once circled. Another mechanism involves stellar encounters. Sometimes a star from outside the system passes too close, its gravity disrupting the delicate balance of planetary orbits. In dense stellar environments like globular clusters or the galactic core, where stars are packed closely together, these encounters are common enough that they might eject planets regularly populating the galaxy with wanderers. And in rare cases, a star's own evolution can create rogues. When a massive star goes supernova, the explosion can impart such a powerful kick to any surviving planets that they're thrown clear of the stellar remnant, sent tumbling through space at velocities high enough to escape the gravitational well entirely. What's remarkable is how many rogue planets there might be. Early estimates suggested there could be as many rogue planets as there are stars in the Milky Way, roughly 100 billion. More recent models, based on observations and simulations, suggest the number could be even higher, possibly trillions. For every star with a stable planetary system, there might be dozens of orphaned worlds drifting between them, outnumbering bound planets by a significant margin. If that's true, it means rogue planets are the norm, not the exception. It means most planets don't have the comfort of a sun. Most worlds exist in darkness, moving through the void in isolation, carrying only the faint, residual heat of their formation, cooling degree by degree, year by year, until they reach thermal equilibrium with the cosmic microwave background radiation, the coldest temperature anything can naturally achieve. Imagine living on a rogue planet if life could exist there, which seems almost impossible, but perhaps not entirely. Without a star, there's no sunlight to drive photosynthesis, no external heat source to maintain liquid water on the surface. But deep beneath the surface, radioactive decay in the planet's core could generate warmth enough to melt, ice create subsurface oceans, sustain hydrothermal vents where chemosynthetic organisms might thrive. On Earth, we've found life in the deepest ocean trenches, miles below the surface, clustered around hydrothermal vents, where no sunlight penetrates, feeding on chemical energy from the planet's interior. If life arose on a rogue planet under similar conditions, it would be entirely independent of stars, deriving all its energy from the planet itself, from the slow radioactive decay of uranium, thorium, potassium elements that warm the interior and will continue doing so for billions of years. Such life would never see the stars. It would exist in perpetual darkness, blind perhaps, or bioluminescent, creating its own light in the absence of any external source. It would have no concept of day or night, no seasons, no astronomical cycles to mark time. Its evolution would be slow-driven, not by changing conditions, but by the gradual cooling of the planet, the slow decrease in available chemical energy as radioactive elements decay and heat production wanes. And eventually, inevitably, the planet would grow too cold. The vents would shut down, the oceans would freeze, and whatever life existed would face extinction. Not from a sudden catastrophe, but from the universe's slow descent into entropy. The thermodynamic reality that all energy gradients eventually flatten, all heat eventually dissipates, all complexity eventually unravels. PSO J318.522 is another rogue planet discovered in 2013, about 80 light-years from Earth. It's roughly 8 times the mass of Jupiter young, by planetary standards only about 12 million years old. And it's glowing. Faintly, yes, barely detectable, but glowing nonetheless, emitting infrared radiation from heat still trapped in its atmosphere, warmth left over from the gravitational collapse that formed it. Scientists estimate its surface temperature at around 1,200 degrees Fahrenheit, hot enough to emit visible light in the deep red spectrum, though not bright enough to see with the naked eye. This planet is still cooling from its birth, radiating energy into space, a dying ember floating through the darkness, visible only because it hasn't had time yet to grow cold. PSO J318.522 challenges our understanding of planetary formation. Most planets form from the disks of gas and dust that surround young stars accumulating material through accretion until they reach planetary mass. But PSO J318.522 doesn't have a star. It formed alone, or at least it's alone now, floating freely through space. Did it form from a collapsed cloud of gas the way stars do, but fail to accumulate enough mass to ignite nuclear fusion, leaving it stranded as a substellar object? Or did it form around a star and then get ejected, cast out so early in its life that it never had time to settle into a stable orbit? We're not sure. The data doesn't give us a clear answer, but its existence suggests that planet formation is even more diverse than we thought, that planetary mass objects can arise through multiple pathways, not all of them involving stars. And here's the unsettling part. Rogue planets are nearly impossible to detect. They don't emit visible light. They don't reflect light from a star because there's no star nearby to reflect. They're dark cold, moving silently through space, invisible to most of our telescopes. We've only found a few dozen confirmed rogues, and those were detected using indirect methods, infrared observations that pick up faint heat signatures or gravitational microlensing events, where a rogue planet passes in front of a distant star, and its gravity briefly magnifies the starlight, creating a temporary brightening we can measure. But for every rogue we detect, there are likely thousands, maybe millions, that pass unnoticed too cold to emit detectable infrared, too far from other stars to cause microlensing events. Think about that. There could be rogue planets drifting through our solar system right now, passing through the outer reaches beyond Neptune, moving too slowly and too dimly for us to notice. They could pass within a few light years of Earth, close enough that interstellar space travelers, if we ever become such, might encounter them, dead worlds floating in the darkness, offering no resources, no warmth, no reason to stop, just silent reminders of how common exile is in the cosmos. How many stars has PSO J318.522 passed in its 12 million years of wandering? How many planetary systems has it drifted through unseen and unremarked, a ghost among the living? Do you ever think about loneliness on a cosmic scale? We talk about being alone in the universe, about the Fermi paradox, about the silence we hear when we search for extraterrestrial signals. But rogue planets embody a different kind of loneliness. They're not searching for signals. They're not capable of wondering where everyone else is. They just drift governed by momentum and gravity, following paths determined by events that happened millions of years ago. Events they have no memory of, no awareness of, no ability to change. They'll drift forever, or until they're captured by a passing star, or until they collide with something, or until the universe expands so much that even galaxies are isolated from each other. And then they'll drift through an even emptier void, surrounded by nothing, not even distant stars to mark the passage of time. There's something almost poetic about that, though. Rogue planets don't belong anywhere. They're free in a sense, unbound by gravity, unshackled from the tyranny of orbits. They go where physics takes them, indifferent to borders, to star systems, to galactic structures. They're the universe's wanderers, its nomads, its exiles. And maybe that freedom comes at a cost. Maybe being unbound means being alone. Maybe the price of independence is isolation. Maybe orbiting a star, being part of a system, having a place, even if that place is fixed and predictable, is better than drifting endlessly with no anchor, no home, no light to guide you. But perhaps that's a human interpretation. Perhaps planets don't experience loneliness. They don't feel. They don't yearn for companionship or warmth or meaning. They simply exist, moving through space according to the laws of physics, indifferent to whether they're part of a system or adrift in the void. The loneliness is ours. We project it onto them because we see ourselves in their isolation, because we fear being cast out, being alone, being forgotten. Rogue planets remind us of how fragile our connections are, how easily we could be separated from the things that anchor us, how vast and indifferent the universe is to our need for belonging. And yet, knowing that rogue planets exist, knowing that worlds can survive without stars, expands our understanding of where life might arise. If planets can have subsurface oceans heated by internal radioactivity, if they can maintain liquid water and chemical energy sources without any external input, then the habitable zone around stars isn't the only place to look for life. Rogue planets might host biospheres hidden beneath kilometers of ice, thriving in darkness, evolving in isolation, unaware that stars exist, unaware that other worlds orbit in warmth and light. The universe might be full of life we'll never detect, not because it's too far away, but because it's hidden, buried living, in places we haven't thought to look, on worlds we can barely see. The rogues teach us that exile is common, that wandering is normal, that most planets perhaps don't have the privilege of orbiting a star, of experiencing dawn and dusk, of being part of something larger. They're alone. They're cold. They're dark. And they endure anyway, moving through the void, carrying whatever history they have, whatever scars they bear from their ejection, whatever potential they hold for warmth and life deep beneath their frozen surfaces. But our journey through strangeness is nearing its end. We've seen planets that rain glass and iron planets where ice burns, planets with impossible orbits, giants that defy physics ancients, that remember the early universe worlds made of water and diamond, and now rogues that wander alone. Each one has expanded our sense of what's possible, shown us how varied and strange the universe truly is. And now, as we prepare to close this quiet journey, let's turn our gaze back toward home, toward Earth, toward the one planet we know intimately, and ask ourselves what all this strangeness teaches us about the world we call our own. We've traveled far tonight across light years and impossibilities past planets that defy logic and worlds that challenge everything we thought we understood. We've seen glass rain sideways at impossible speeds, ice that burns without melting orbits so chaotic they seem drunk on gravity's randomness. We've visited giants inflated like cosmic balloons, ancients that remember a universe we can only study in equations, oceans deep enough to drown continents and diamonds, larger than Earth's moon, locked away in planetary cores. We've followed rogues into the darkness, worlds exiled from the warmth of stars, drifting alone through the void, with nothing but their own fading heat for comfort. And now, after witnessing all that strangeness, all that hostility, all those environments where survival seems not just difficult, but cosmically absurd, let's come home. Let's look at Earth again, not with the familiarity of lifelong residents, but with the eyes of someone who's just seen what else is out there. Because if there's one thing this journey has taught us, it's this: Earth is not normal. Earth is not the template. Earth is not what planets are supposed to be like. Earth is the strange one. Think about it. We live on a planet where water falls from the sky as gentle rain, not as molten glass or liquid iron or vaporized rock. Where that rain collects in oceans shallow enough to see the bottom, in places warm enough to swim, and stable enough to have existed for billions of years, without boiling away or freezing solid. We have land actual solid ground. You can walk on continents that rise above sea level, mountains and valleys and plains that offer geographic diversity. Most water worlds will never know. We have an atmosphere you can breathe without being crushed, poisoned or asphyxiated, composed of nitrogen and oxygen in ratios that support combustion, enable respiration, and create a sky that scatters blue light during the day and reveals stars at night. Our orbit is nearly circular, which means our distance from the sun varies by only about 3% throughout the year. 3%. Compare that to HD 2782b swinging between Mercury's orbit and Mars's orbit in a single year, experiencing temperature swings that would vaporize oceans and then freeze atmospheres solid. Earth's orbit is so stable, so predictable, that we can calculate its position thousands of years into the future with extraordinary precision. We have seasons, yes, but gentle ones caused by our axial tilt, not by wild variations in solar distance. Spring follows winter. Summer follows spring. The cycle repeats reliable, calming, giving, lifetime to adapt, time to prepare, time to evolve strategies for surviving the transitions. We orbit one star, just one, not two stars circling each other in a cosmic waltz, creating complex lighting patterns and unpredictable gravitational tugs. Not a pulsar blasting us with radiation. Not a red giant slowly expanding to swallow us. A single middle-aged, remarkably stable yellow dwarf star that's been burning at roughly the same luminosity for 4.5 billion years and will continue doing so for another 5 billion. The sun doesn't flare violently. It doesn't pulse. It doesn't have a companion star that causes periodic eclipses. It just sits there, fusing hydrogen into helium, radiating energy into space at a steady life-sustaining rate, asking nothing in return except that we appreciate the photons. We have a moon, a large moon, proportionally one of the biggest moons relative to its planet in the entire solar system. That moon stabilizes Earth's axial tilt, preventing it from wobbling chaotically the way Mars's tilt does, which would cause extreme climate variations, ice ages followed by hothouse conditions, swings so severe that complex life might never gain a foothold. The moon also drives our tides, mixing ocean waters, creating intertidal zones, where life transitions between aquatic and terrestrial environments, where evolution experiments with amphibiousness, where the boundary between sea and land becomes a laboratory for adaptation. Without the moon, Earth would be different, more chaotic, less stable, possibly less alive. We have a magnetosphere generated by a liquid iron core that churns and convects, creating magnetic fields that extend tens of thousands of kilometers into space, deflecting the solar wind, protecting our atmosphere from being stripped away, the way Mars's atmosphere was billions of years ago. That magnetosphere is invisible, intangible, easy to forget about, but it's essential. Without it, the sun's charged particles would erode our atmosphere, break apart. Water molecules send hydrogen escaping into space, leave us dry, airless, exposed. The magnetosphere is a shield we never see operating, silently, constantly keeping the hostile environment of space at bay. And then there's the chemistry. Earth is rich in heavy elements: iron, silicon, magnesium, carbon, oxygen, nitrogen, all the building blocks of complex molecules, all the ingredients necessary for life as we know it. We're not metal poor like TOI 561b, struggling to form rocky structures from limited materials. We have an abundance of periodic tables worth of elements to work with, deposited here by supernovae that exploded billions of years before the sun formed, enriching the molecular cloud from which our solar system eventually coalesced. Every atom of carbon in your body, every atom of oxygen you breathe, every atom of iron in your blood was forged in the core of a dying star and scattered into space through a violent explosion. Then gathered here on this small planet, assembled into structures complex enough to wonder about their own origins. When you put it all together, the stable orbit, the single sun, the protective moon, the magnetosphere, the breathable atmosphere, the liquid water, the abundant heavy elements, the moderate temperatures, the predictable seasons. It starts to seem less like a planet and more like a miracle. Not a religious miracle, but a statistical one. A confluence of so many unlikely factors, each one necessary, each one rare, each one somehow present here on this one world, in this one star system, at this one moment in cosmic history. Scientists call it the rare earth hypothesis. The idea that while simple life might be common throughout the universe, complex life, the kind that builds ecosystems and technologies and civilizations, requires such a specific set of conditions that it might be extraordinarily uncommon. Earth-like planets, truly Earth-like, with all the features we've described, might be vanishingly rare, scattered across galaxies in numbers, so small that the distances between them are effectively insurmountable. We might be alone not because life can't arise, but because the conditions for complex life are so stringent, so demanding, that most planets fail to meet them. But here's the beautiful part. Even if we're alone, even if Earth is the only planet in the galaxy hosting intelligent life, the strangeness doesn't diminish. It amplifies. It means we're not just rare, we're unique. We're the universe's way of knowing itself, of asking questions, of looking outward and wondering what else is out there. We're the cosmic accident that became conscious, the statistical fluke that learned to do mathematics, the improbable assembly of atoms that figured out how to build telescopes and spacecraft and particle accelerators. And if that's all we are, if we're the only ones doing this, then our responsibility becomes even greater. We're not just preserving a species, we're preserving the universe's only known instance of self-awareness. Do you feel the weight of that? The fragility? We exist on a planet that's gentle enough to allow us to thrive, rare enough to be precious, and vulnerable enough to be destroyed by our own actions. Climate change, nuclear war, ecological collapse, pandemics. Any of these could end our experiment in consciousness, reduce Earth to just another planet. Lifeless, silent, indistinguishable from the billions of other rocks orbiting billions of other stars. And if we fail, if we don't manage to survive our own technological adolescence, the universe won't notice. It will continue expanding, stars will continue burning, galaxies will continue colliding. And the fact that one small planet once hosted a species that asked questions and wrote poetry and built cities will be lost, erased, forgotten, as if it never happened at all. But it doesn't have to be that way. We have the knowledge. We understand the threats. We know what needs to change. The same intelligence that allows us to study distant exoplanets to measure their compositions and orbits and temperatures can be turned inward towards solving our own planetary challenges. We can choose to protect the atmosphere, preserve the biodiversity, stabilize the climate, ensure that future generations inherit a world as gentle and habitable as the one we were born into. It's not easy. It requires cooperation. Sacrifice, long-term thinking, all things our species struggles with. But it's possible. And given what we've learned about the alternatives, given what we know about how hostile most planets are, the choice seems clear. Earth's strangeness is a gift. The gentle rain is a gift. The breathable air is a gift. The stable orbit, the protective moon, the magnetosphere, the oceans, the continents, the forests. The diversity of life that fills every available niche, all of it is a gift. An improbable alignment of cosmic factors that won't last forever, but has lasted long enough for us to arise, to look around, to appreciate it. And maybe that appreciation, that sense of wonder and gratitude is what will save us. Maybe recognizing how rare and precious our home truly is will be enough to motivate us to protect it, to treat it with the care it deserves, to ensure that the strangeness we call home endures for as long as physically possible. The strangest planets we've discovered, the ones that rain glass and burn ice and wander alone through darkness, they're not just curiosities. They're mirrors. They show us what we're not, what we could have been, what we might still become if we're not careful. They remind us that the universe doesn't owe us anything, that habitability is not a right but a circumstance, fleeting and contingent, dependent on factors beyond our control and factors very much within it. They teach us humility. They teach us gratitude. They teach us that normal is a fiction, that every planet is strange in its own way. And Earth's particular strangeness happens to be exactly what we need. So, as we close this journey through the cosmos, as we drift back from the edges of the known and the impossible, let's carry that lesson with us. Let's remember the planets that can't sustain life, that never could, that exist in conditions so extreme they mock the very idea of habitability. Let's remember how lucky we are, how statistically improbable our existence is. How many things had to go exactly right for us to be here? Now breathing easily, listening to these words, contemplating the vastness of space from the comfort of a world that doesn't actively try to kill us. And let's choose to protect it, not because we're noble or virtuous, but because we understand what the alternative looks like. We've seen it. We've studied it. We've cataloged thousands of planets, and almost none of them are places you'd want to live. Earth is. Earth is gentle. Earth is rare. Earth is home. And maybe recognizing that will be enough. Thank you for joining me on this quiet drift through the cosmos. Thank you for your curiosity, your patience, your willingness to explore the strange and the wonderful and the impossible. The universe is vast, filled with mysteries we have barely begun to unravel, and there are countless more stories waiting to be told, more planets waiting to be discovered, more strangeness waiting to surprise us. I hope you'll join me again soon as we continue exploring the gentle science of the night sky. Until then, rest easy. Look up at the stars when you can. Remember how far we've come and how far we still have to go. Sleep well, dream gently, and know that you live on the strangest, most beautiful planet we've ever found. Good night.